Hi everyone, section 1.2 is on maxima and minima of functions. So maxima and minima are those points on a graph like you see here that are the highs and the lows, and those are specific y values for how high or low that function gets. So a couple of formal definitions to get through first. So the first thing is a global max and global min. And then we'll talk about local maxes and local mins. So a global max, the definition for that is that if f of c, so c is just some x value, and that f of c, meaning the y value at that c, is greater than or equal to f of x for any other value of x in the entire domain of the function. So if there's some x value, in this case we're calling it c, that its y value is higher than any of the other ones, then that would be called a global maxima of the function. So a global maximum. If for some value of c, its y value f of c is less than or equal to f of x for any other x in the domain, that would be the global minimum. So this should be review for all of you. You should have done this in math 2 or 3. I'm not sure which one. Minimum. Okay. Global maxes and global mins are also called global extrema. So if you're asked to find the global extrema, you're being asked to find both maxes and mins. Or absolute extrema. So again, just to recap, global is the highest y value for the entire domain of the function. We also have another type of extrema called the local max and min, and that is different because it's just on a certain open interval. So if you look at the definition for global, it's the highest value for all of the x's in the domain. Local maxes and mins are just on some interval, so it doesn't have to be the absolute highest or lowest like this value right here. It's obviously not the lowest y value, but it's just the lowest y value on some domain or some restricted domain. So the definition for local max is that f of c is greater than or equal to f of x for all x in some open interval containing c, and that would be the local maximum. And likewise, if f of c is less than or equal to f of x for all x in some open interval containing c, it's the local min. And another way we describe local mins and maxes together would be called the local extrema. Or the relative extrema, same thing. So those are the formal definitions. Now we can go ahead and get into an example. So the first thing that you need to do right now is use a graphing calculator to graph this function f of x. So go ahead and type that into your y equals. Alright, so I have this video to show what you should see on your calculator, and you'll see that we need to change our window. So we can't see all the y's, so I'm going to make my y's go down even farther, and I can probably close the x's in a little bit to get a better picture of this. So I'm going to change my window from x's to be -5 to 5. -5. And my y's, I'm gonna have that go down to -30 to see if I can get that whole picture. Actually, I'll go -50. And then I'll go up to 30. So there's a more complete picture of the graph This way we'll be able to get all of those maxes and mins. All right. Okay, once you have that graph on your calculator, you can go ahead and sketch the graph on the notes with all of the key points. So the key points are all of the maxes, mins, and intercepts. So we scaled ours out from 0 to 5. And the other way. And then we went up to 30 up here, negative 50 down here. So if we want to graph all of the intercepts, if you go back to your calculator and look at the intercepts, you can see that our function crosses the x-axis at -3. And if you aren't sure, just hit trace and type in -3 and enter, and you should get y equals 0 when you do, just to confirm that. So here's one of our intercepts. And then it looks like it crosses at 1 as well, so I'm just going to type in trace 1, and then I get x equals 1, y equals 0, so that is accurate. And then it also looks like it crosses at 3, so just double check that by tracing when x equals 3. So those are our intercepts. And we've got a y-intercept. And so let me trace when x equals 0, y equals -9. So that's going to be closer to here. It's -9. And then we can sort of sketch a little bit of our graph here. So we go down, across, down, and up. So not the best sketch, but close enough. So I want to label all of my key points now. So this would be -3, 0, 0, -9, 1, 0, 1, 3. And now I want to figure out my maxes and mins. So hopefully you all remember how to do maxes and mins on your calculator. Let me show you for a quick review. All right. So to find the maxes and mins, try and get rid of that glare. You're going to hit second trace for the calc button, and you're going to go down, whoops. Say I want to find a minimum. So I have a minimum down here, select minimum, and then you have go to the left of the minimum, and then it's asking you for the right bound, go to the right of the minimum, guess, hit enter one more time, and then it gives it to you. So our minimum for right there is -1.89, and the y value is -45. That's where the minimum occurs, is -1.88. The minimum itself is the y value, so that min is -45.3. All right, so let's label all of those. So we said this was negative, we'll just round to the nearest tenth. So -1.9, -45.3. And then we've got a maximum here and another min there. So take a minute to figure those out. I would pause the video, just figure those out on your own, and then start playing again to make sure that you've got those correct. So this minimum or maximum right here is actually already labeled because it's our x-intercept. So this is actually 1, 0, and then you have another minimum right here, which you should have found to be 2.4. It occurs when x equals 2.4, and the minimum itself is -6.4. So remember, the mins and maxes are always the y value. Where they occur is the x value. So in this case, the minimum of -6.4 occurs when x equals 2.4. All right, so we've labeled our graph, and we can state the domain of the function. If you look back to our original function, there are no restrictions on a polynomial like this. We can plug in any value of x. So our domain in interval notation would be negative infinity to infinity, or all real numbers. So if you look down at part C, we're going to approximate the global and local mins and maxes for each domain. So we're starting out right here with the entire domain. So we're looking for a global max on the entire domain. And global would mean higher than any other value. So because our function, if you look at the ends of the function, our function increases without bound in both directions. It's going up forever and ever. So there's not any one value that's higher than all of the other ones. So there actually is no global max. If you look for global min, we want a value that's absolutely lower than any other value. And remember, maxes and mins are the y values. So if you look at your graph, this negative 45.3 is the absolute lowest y value this function will produce. So our global min is negative 45.3. For the local max, I'm looking for any local areas where within that one area, one of the y values is higher than all of the other ones. So in this case, right here, we see a turning point. Anytime there's a turning point where the function goes from increasing to decreasing or decreasing to increasing, then you're going to have a local max or min. So in this case, we actually do have a local max right here, and the local max right there is the y value, which would be 0, which might seem confusing because we don't think of the number 0 as being a maximum number, but it's higher than all of the other ones around it because it goes into the negatives. Local min, so we're looking for, again, turning points. Our local min, or our global min, is also going to serve as a local min in that area, so negative 45.3 is a local min, and you can have more than one local min or local max. So this is also a local min right here, and that y value is, this y value, negative 6.4. So we've just listed all of the global and local extrema on the entire domain. So this is going to get a little messy here as we move on, because now we're looking to restrict this just on the domain of negative 2.5 to 1. So if we look at negative 2.5 would be about right here, and to 1, which is right here. So just on that interval, do we have a global max? Do I have one value that's absolutely higher than all of the others on this interval? And it's important to notice that it's a closed interval, so we're including those endpoints of 1 and negative 2.5. So if you follow the function right there, just for that interval, its absolute highest point is right here where x equals 1. So it actually will have a global max on that interval, and that global max is going to be the y value right there, which is 1. Global min would be the absolute lowest value on that interval. The absolute lowest value would be, in this case, the same as it was before, because the global max, or the global min, occurs within that interval. So the global min is negative 45.3. A local max, so locally higher than any other y value in that area. This is going to seem a little weird, but this, and right here where the edge of our boundary is at negative 2.5, the y value at that point is actually going to be higher than any other y value right there on this domain because it goes down from there. So this is actually going to serve as a global max where x equals negative 2.5. So to figure out that y value, if you're looking at your graph, hit trace and then type in negative 2.5 and you'll get your y value of negative 33.7. And then the local min, well, we still have this local min, which was our global min as well, negative 45.3. And that's that. So now we're going to restrict this again on the interval 3 to infinity. So I apologize for how messy this graph is going to start looking. But if I go out to 3, which is right here, here's 3, where x is 3. And we're talking about from here to infinity, so only going to the right. The global max would be the absolute highest y value, but as you see, this function approaches infinity, it will not have a highest value, so there is no global max. The global min would be the y value that's absolutely lower than any other y value on that interval. It's important to note that we are including 3, so we are including this point 3, 0 in our domain, which means that we can include the minimum of 0. That's the absolute lowest y value on that interval. A local max would be the highest y value in some interval on that domain, but there is none because it's only increasing, and it continues to increase. A local min would just be the smallest y value in some interval on that domain, and it's going to be the same as our global min, which is 0. So the big change from this example to the next one is that now we're not including 3. So we're not including x equals 3, so you can imagine this being an open circle, and then we're continuing on to infinity. So again, a global max isn't going to exist because there's no value higher than all the others. A global min would be a value that's absolutely lower than all of the other ones, but because we can't include x equals 3, the function is going to get infinitely close to that, and it's going to continue decreasing, but never get to a lowest value, so there is no global minimum either. Local max, just like our previous example, we aren't going to, have one of those. And then if we look for a local min, again, because we aren't including this endpoint right here, the function is going to be getting infinitely close to that minimum of 0, but because we are not including 3 in our domain, we can't ever reach that minimum. So there is no local or global extrema on this domain, which seems a little strange, but hopefully it makes sense. Okay, so hopefully all of this was mostly review for all of you when you're talking about just identifying and finding local and global extrema and those y values that are the extrema and the x values where they occur. So now we are problems, which usually freaks people out, but I can assure you that with some practice, you will get the hang of this. So I'll talk you through both of these, and these are a little overwhelming at first, and people usually struggle with them, but I will say that if you remember to look at the big picture and keep that end result in mind, and with doing some practice problems, I think you'll all be just fine. So first, let's read through it. So a gardener wants to enclose his garden plot with fencing in a rectangular region that measures 500 square yards. So we know he wants 500 square yards of space in his garden. He wants to use the side of his house as one side. So let's draw a picture here. There's the side of his house. So he only needs to fence in 3 sides. So there's his house. Here's 3 sides of a garden. And he wants to determine the least amount of fencing needed. So in these word problems, the first thing you should probably point out is what are you trying to minimize or maximize, because this section is on maxes and mins. So we're going to come up with a function, and in this case we're going to be minimizing the amount of fencing, and the amount of fencing around the garden would be the perimeter. So we want to minimize the perimeter. That means all we need to do is come up with a perimeter function, plug it into our calculator, and minimize it. So if we label these, so let's call those sides X and this side Y. So the perimeter of fencing we need to calculate in this case is just going to be 2x's plus 1y. So our perimeter function is 2x plus y. The only problem with this function is we can't type this into our calculator because there are two variables. So that's not helpful to us yet. However, if you look at the problem, we were told extra information that's going to help us. We were actually told the area. We were told the area of this. He wants the area to be 500. Luckily, we know the formula for area of a rectangular shape, so which would be x times y. So we have this additional formula or equation here that is 500, the area equals x times y. That is going to be our key, because if we can solve for x or y, we can plug it in to our perimeter function so that we will only have one variable. So let's solve for y here by dividing both sides by x. You get y equals 500 divided by x. So this all stems from the area function. But the good thing is, since I can represent y just in terms of x, I can take this whole thing right here and plug it into y right there. So I can rewrite my perimeter function, p, and since I'm using the variable x, I'll call it p of x, equals 2x plus, now instead of y, I can write 500 divided by x. So now I have this function, and this only has one variable, x, and I can plug that in and graph it and find the minimum value of p, which would be my output, or the y value, and that would be the least amount of fencing to use. So let's go ahead and type that into your calculator. Okay, when you plug in, sorry about the lighting, when you plug in this function, our perimeter function 2x plus 500 divided by x, and you graph it in the standard window Zoom 6, you get absolutely nothing. The reason for that is because we need to change the window to fit the context of our problem. So if we, let's see, the area is 500 square yards. Our function is measuring perimeter, and well, first of all, we don't care about negative x value, so my min is going to be 0. My x max, remember x in this case is representing that length of two of those sides. So what would make sense to put in for a length of a garden plot? I have no idea, but I'm just going to say, let's say 50 yards. And then I'm going to scale that by tens so I don't have too many lines on my axis. The y values, since this is a function of perimeter, y is going to represent that perimeter. I obviously don't need negative values for that. I'm not sure what that perimeter might be, but it's definitely going to be a large number if the area is 500. So I'm actually just going to type in a perimeter of, actually probably higher than 500. I'm just going to type in 1,000 and see what happens. So finding the appropriate window is kind of a guess and check game, but think about the context of the problem. I'm going to scale that by 50s and then graph it, and let's just see what we get. So that's a pretty good picture. I'm going to change it a little bit. You can see the minimum right here, but it's pretty drawn out. So I'm actually going to go even further on the x's to see if I can get a better picture. I'm going to do 150. So I have a more defined minimum now. So don't panic when you graph some of these and you have no graph. Just think about the context and play with the window and see if you can get to it. So that's our window, and now we can minimize the function. So second trace to get the calc functions, the min and max. we want the minimum. Go all the way over here. With these gradual changes, make sure you get all the way to the left and right of that dip. And so our minimum occurs when x equals 15.8. The minimum itself, that minimum perimeter we're looking for, is 63.2. Okay, so I'm going to sketch a quick graph of what we just had here, something like this. And then we found our minimum right here. And we said that is 15.8, comma, 63.2. So it's important to understand what those values represent. This is the x value. And we already, this is our x, which is the length. So let's say the length is, to get that minimum perimeter, has to be 15.8 yards. Our actual minimum perimeter is 63.2. So 63.2 yards is the answer for what is that smallest perimeter. And to get that smallest perimeter, the dimensions would be a length equals 15.8 yards. The question is, how do I figure out what this value is going to be? I do need that dimension as well. So in order to find that out, if we know we have this right here, we solved for y in terms of x, so we can actually just plug our x value of 15.8 back in there and get y. So the y would be 500 divided by 15.8. So that would be about, let's see, .6 yards. So if, hopefully you can see in this jumbled mess, the minimum perimeter, 63.2 yards. The dimensions to get that perimeter would be a length of 15.8 yards and a width of 31.6 yards. So that is the solution to that problem. Okay, this next one, same idea, different figures. So a container manufacturer wants to create a cylindrical metal can, so a paint can, that holds 1 quart of paint with a little extra airspace at the top. So the manufacturer decides 58 cubic inches is the best volume for this can. So cubic inches means we're talking about volume. So this is going to be the volume. And the manufacturer wants to keep the cost of materials as low as possible. So he wants to minimize the cost of materials to make this paint can, and the materials to make this is all of the surface area. So we want to minimize what that would be. So minimize the surface area. What that means is we need to come up with a function for surface area and plug it into our calculator and minimize it. So the surface area of this cylinder, let's just break it down. So that would be the area of the top and bottom. So let's think of that separately. Top and bottom. And then we're going to add that to the area of the lateral area, which is just all the way around, which if you cut a cylinder down the side and stretched it out, it's basically just a rectangle. So that's the lateral area. And we need to figure both of those out, and that will be our function for surface area. The top and bottom is just a circle, and the area of a circle, hopefully you all know, is pi r squared. But we have top and bottom, so we need 2 of those. So our surface area equals 2 of the pi r squareds. So 2 pi r squared. That's the area of the top and bottom. We also need the lateral area, which would be the base of this, which the base of that, or you can think of it the distance around, that's circumference. So if you think back to formula for circumference of a circle, that is just 2 pi r. So that would be the length of the base, and then times the height. So that would be 2 pi r times the height. Okay, so we've just built the formula for surface area of this paint can. So if you're concerned about that, don't worry about it. You can rewatch how to build the surface area formula for a cylinder, but what I want you to get out of this is how to minimize this. The problem with this function is that we've got two variables. Our variables are r and h. We need to represent one in terms of one of the others so that we can actually plug this into our calculator. The good thing is that we were given an extra piece of information about this can, and that would be the volume. So you're always going to use that extra piece of information to your advantage. So we know for sure that the volume is 58. So volume of this can is 58 cubic inches. So we need to know the volume formula to use this. So the volume equals for any cylindrical or any prism, it's the area of the base times the height. So area of base times the height. That's volume for any prism. So our volume, why do I keep doing that? 58 equals area of the base, again, which is just a circle, so 2 pi r squared times height. So now we have this extra formula that we can use, solve for h or r. In this case, it's definitely going to be easiest to solve for h because all you have to do is divide by pi r squared. So we have h equals 58 divided by pi r squared. So what that means is we have this whole thing, which is equivalent to h, that we can plug in right here, and then our surface area formula will only have one variable. So this is going to look a little crazy. I'm going to rewrite our surface area without using h. I'm going to use this instead. So it's 2 pi r squared plus 2 pi r times this whole thing, 58, divided by pi r squared. So we've come up with this new function for surface area in terms of only r, which will be our x when we plug it into the calculator, and you can minimize that. So you can simplify this a little bit, or you can type it into your calculator as it is. There's pros and cons to both of those. If you try to simplify it a little bit, you have room for more error in that simplification process. But if you don't and you try and type it in like this, you have more room for error when you're actually typing it into your calculator. This one you can simplify pretty easily if you look at this section right here. I can cancel out my pi's, and I can cancel out 1r, leaving 1 on the bottom. So what I'm going to type into my calculator is this: 2 pi r squared plus, and then I've got 2 times 58. So you might as well just type in 116 over r. So that's the simplified one, and you can go ahead and type that into your calculator. Alright, when you type this into your calculator, again, I just typed in our simplified version right there. When you hit graph, or the standard window zooms 6, is you get this, which doesn't make any sense because remember our x value is representing r, which is radius, so we don't want any negative radii, and our y value is representing surface area. So this window isn't going to work for us. I only care about positive radius values. My x values, remember that's representing radius of a paint can, so think logically about radius of a paint can. I can't imagine it being that high. I do want a complete picture though. So we're not going to have a 20-inch radius, but let's just see if we can get a full picture of that. And then my y min, remember that's representing surface area. I'm going to start at 0. As far as my y max, I'm not totally sure what that surface area might be in cubic inches. I'm just going to pick a number, a pretty high number, and see if I can get a good image. And I'm going to change my scale to 25. So let's see if that produces a graph. There we go. So that's a pretty good graph. I definitely didn't need to go out that far on the x's. So you could change that if you want, but it really doesn't matter. We've got a good picture here. So now we can minimize that and figure out what that smallest amount of surface area. Now I just need to find my cursor. So get that left bound value, the right bound value. We've got our minimum about 2.183. So go ahead and sketch your graph, label the minimum, and then we'll talk about those values. Okay, so we had this graph. It looked something like this. The only reason these are here are just so that we can label our key points and make sure we understand what those mean. So that x value was about 2.1. The y value was 83, if we round. Wait, yep, 83. Okay, so it's important to understand what those numbers represent. Remember, those x values were these r's. So this is the radius of our can. That's important because we need to know the dimensions of the can to get the minimum surface area. So the dimensions of the can that we want would be a radius of 2.1 inches. That would produce a surface area, the minimum surface area of 83 square inches. The only thing is we still need the height. And if you look back right here, there's always going to be that last dimension that you need to find, but you will have already solved for it somewhere else in the problem. So we solved for it right there. So we're actually just going to plug in the radius of 2.1 right there to get the height. So you would just want to punch in your calculators 58 divided by pi times 2.1 squared. And you should get 4.2. So it would be 4.2 inches tall. So those are the dimensions of the paint can. Alright, there's one more of these problems. Next page. I would encourage you to pause the video and at least attempt to get started on this. The hardest part of these problems is getting started. So if you can read through the problem, figure out what you're trying to minimize or maximize, come up with that formula, at least getting started on your own, since that's what you're going to need to be able to do after all of this. So I encourage you to pause the video now and try to get through this one, and then you can play through it just to check your work with mine. Okay, so we have a box with a square base and no lid, so only a bottom, no top, and it must have a volume of 3,000 cubic inches. Find the dimensions of the box with the given volume and the smallest surface area. So this is similar. Remember, you want that big picture result. We want to minimize the surface area. So we'll need a surface area for this box with a square base. So let me do my best to draw a picture of this. I'm not an artist. Oh gosh. Okay, here's my box with a square base. All right, so it's a square base. That's super helpful to us because we know these dimensions will be the same. We don't necessarily know the height. We just know that the base is a square. So the surface area of that, and I'm always surprised to find each year that finding the surface area of a figure like this is more of a challenge for my students than I expected. So let's just talk through the surface area formula. The surface area of this, the area of the surface, let's first just talk about the area of the base of that right here. That would be x squared. Then I want the area of, let me change colors, all of these four sides, the back and this side. They're all going to be the same, so if I can find the area of one of them, I can find the area of all of them and multiply it by 4, and the area of one of those sides is just h times x, or x times h. And then we're not including the lid because it said no lid. So this is the surface area formula. So surface area that we want to minimize is x squared plus 4xh. That's all we need to do to minimize. The problem is we have two variables. We have x and h. I can't type that in to minimize with two variables. So now we need to use this. So we were told that the volume of this figure is 3,000 cubic inches. The volume for a figure like this is just the area of the base times the height. So we know that the area of the base is x squared times the height. So that's it. We've got this new formula here, and we can solve for h by dividing both sides by x squared. So we know that h equals 3,000 divided by x squared. This is super helpful to us, and now we can take this expression and plug it in for h in our surface area formula, and then we have something in one variable that we can plug into our calculator. So here is our surface area formula with only one variable. X squared plus 4 times x times h, and instead of h I'm typing in this whole thing, 3,000 divided by x squared. Now here, this is our final formula. You can plug that into your calculator as it is, or you can simplify it a little bit. I like to simplify it. Remember, there's pros and cons to both. If you simplify it, you risk making a mistake in that process. If you type it into your calculator as is, you just have extra numbers and extra buttons to push, and there's room for error there as well. So decide what you prefer and just do it your way. I can cancel out this x with one of those x's, and then I can multiply 4 times 3,000. So that ends up being 12,000, and then I'm just left with 1x. So I like the simplification process, so I can just type that into my calculator. So go ahead and type that into your y equals. X squared plus 12,000 divided by x. If you graph this on your standard window, you won't see anything useful. So here's what I get. You need to change your window. Remember, we're talking about dimensions of a box. So negatives don't make sense. X is representing the length of the base, the square base of that box. I have no clue. Let's just go up to 30 and see what happens. I think it's better to go too high, and then you can go down rather than not go high enough. Okay. Remember, the output is what we're trying to minimize, which is surface area. Surface area of a box, let's try 500. Let's just see what happens there. Scale by 25s and graph. So nothing is being graphed right now with a surface area max of 500. That means this is a much larger box than I anticipated. So I'm going to go big. Go big or go home. All right, it's a large box. Okay, so now I have a piece of the graph. We definitely have a minimum here, but it's pretty gradual. So I'm going to extend and go even farther out on my x's. X max. I'm going to go up to 100. Scale by tens. And then I have a more defined minimum there. So you can see that the process for finding the best window is just a process, and you're gonna have to toy with it a little bit. Okay. Find your minimum. So 18.2 is the x value where our minimum of 990.6 occurs. Remember, that is the minimum surface area for this box. All right, so I'm going to sketch a quick graph. Something like that. I had this point right here, which was 18.2. Y value 990.6. Okay, remember the important part after you get to this is knowing what these values even mean. We were minimizing the Y value, and that represents surface area. So our minimum surface area is 990.6 inches. And to get that surface area, that means the length of our bases, so I don't know, I guess we'll call that length, would be 18.2. And then we still need to know the height of our box. And length is also width because it's a square base, so that only leaves the height. Remember that last dimension you always will have already solved for here. So all we need to do is go back to that and plug in our value of x, which is 18.2, and figure out what h is, which you should quickly find to be 9.1 inches. So those are our dimensions to minimize the surface area of that box, and that's it. So you've seen 3 examples of this. Don't forget your final end result. So that's what your goal is. So don't lose sight of that in all of this jumbled mess that happens in the process. And if you don't have a graphing calculator, I forgot to mention, send me a message and I can meet up with you at Linworth and sign one out to you that you can use for the summer. And I also apologize for the length of these videos. They've been much longer than I anticipated. The next section shouldn't be quite as long as this. It's not as much of difficulty in the type of problem that you'll see. So, all right, until next time.